Welcome back to Number Sense Academy, and we are going to talk about quadratic equations. So this is an intro to quadratic equation. It's a big topic, so we're going to take it one step at a time to make sure that we have full understanding about this very broad topic in mathematics. I think it's a very broad topic. There's just so many elements to it, so many components that you have to take your time and dive into each bit. If you're in high school math, you might do this in grade 9 or whatever, but it'll probably show up for the rest of your life if you take mathematics. Whether it's in business, whether it's in engineering, um, it'll pop up. So we're looking at quadratic equation. So what I found out is that quadratic, this word, or maybe the whole word, not just that word, the root word is a Latin word called quadrare. I don't know if that's how you say it. And it actually means to square. Okay. And once we know that part, that kind of sends or lends makes it easier to deal with the rest of the topic. I was confused when I saw the word quadratic. Nobody told me that it came from quadrare, but now that I know that it means to square, then it makes it easier for me to understand. Might not be the same for you, but nonetheless, I'm saying too much of the wrong thing. Okay, so the standard form for a quadratic equation is ax squared plus bx plus c equals 0, where a, b, and c are constants, or there'd be coefficients, right, in front of the terms, but a cannot be 0. If a is equal to 0, right, then all we're going to end up with is bx plus c. And now this is just a line. This looks like mx plus b, right? So now it's just a line, and we don't no longer have the squaring. If a is equal to 0, then we've eliminated the whole squaring part. All right, so that's the first thing. Another thing about quadratics, because of this 2 right here, because of this 2, it's said to be an equation of degree 2. An equation of degree 2, because this exponent, there's a 1 here and there's a 0 here somewhere. Because this exponent is the biggest exponent, it's a 2, so it's of degree 2. So let's look at some quick forms of quadratic equations. So if I take just a quick example, 3x squared minus 5x plus 6 equals 0. This is quadratic. If I have x squared plus 5 equals 0, this is also quadratic because I have my x squared. Here I have the x squared. If I have 2x plus 3, this is not quadratic, right? Because the exponent here is a 1. It's not enough. It needs to be 2. What if I have x squared is equal to 3x plus 2? So this is just the rearranged form of the standard form. This is quadratic. And my first indication is the fact that there's a 2 there. What about 2 times w squared minus 2w is equal to 5? Yep, this is quadratic. Because of this 2. It's also quadratic. And if I have b times b minus 1 is equal to 3, this is also quadratic because I can distribute this b to these two numbers, and I'm going to end up with b squared minus b is equal to 3. And there's my 2. So it is quadratic. Okay, so the only one that wasn't quadratic was this one. And we know why, because of that. Okay, so we mentioned that in standard form, we have ax squared plus bx plus c equals 0. Or we could write it as y is equal to ax squared plus bx plus c. Okay, so that's standard form. And if you have an equation that's in this form, if you just, teacher gives you an equation and it's in this form, then right away you could already deduce a lot of information about what the graph will look like and how the graph will behave. First of all, you can tell if the quadratic has a maximum or minimum. Okay, and the way you can tell is if the sign in front of a is negative. Okay, so if you have the sign in front of a is negative, so the sign in front of a is negative, then you'll have a maximum, because the graph opens downward. Okay, if the sign in front of a is positive, just the sign, we don't care about the magnitude, we don't care about the number that's in front of a, or what a is, I should say. We don't care if a is 3 or half or a million. We just care about the sign. So if the sign is positive, then we have a minimum, and the graph opens upward. So that's starting from, from the front. Now, when we look at A, we could tell how the graph behaves around the x-axis. So we're going to call it behavior around the x-axis and the y-axis. What do I mean? So if A is a fraction, if A is a fraction, that means it's a number between -1 and 1, right? So all fractions sit between -1 and 1. If A is a number between here, then the graph is going to be like compressed towards the x-axis. Almost like a flower that's kind of opening its petals and opening them really wide. It's going to be compressed toward the x-axis. If A is a number bigger than 1, so greater than or equal to 1, or it's less than or equal to -1, then we're going to say it's compressed toward the y-axis. All right. So now let's look at what you probably asking, what am I talking about? We haven't even looked at what the graph looked like. So let's look at some examples that will kind of demonstrate these behaviors. All right, so we're going to start with the general form, but we know that our general form is y equals ax squared plus bx plus c. But what if we only have, like, we don't have the bx plus c part? If we have, say, y equals x squared. This is still a quadratic equation because this satisfies the rule of a quadratic equation. So what happens when we only have a quadratic equation that's y equals ax squared? So I'm going to take y equals x squared, and where in this case a is 1, right? We don't have a value for b. We don't have a value for c in the equation, so we could automatically assume that So we know that a is 1. So it's going to be 1x squared plus 0x plus 0. Right? So that's what that does. So if I was to create a table of values for y equals x squared, okay, so I'm going to pick -3, -2, -1, 0, 1, 2, and 3. All right. If I substitute these values in this equation, I'm just going to do it once. So if I have y is equal to x squared, then I make it -3 squared, I end up with 9. Okay, so -2 squared is 4, this is 1, this is 0, 1, 2 squared is 4, and 3 squared is 9. All right, so a couple things we already noticed, or you should already notice. From this equation, the c in general form, the c is the y-intercept. The c is the y-intercept. Okay, so if you have an equation in standard form, when you see the c by itself, or the c, whatever that value is, that is the y-intercept. Because if you let, for the y-intercept, we let x equals 0. So we're going to let x equals 0. If I sub that into this equation, I get a times 0 squared plus b times 0 plus c. So I get 0 plus 0 plus c. So y is equal to c. At the y-intercept, remember, x is always 0 for the y-intercept. So that's my y-intercept. If I look in my table of values, when x is 0, y is 0. Okay, so that makes sense. The y-intercept is 0. So it's not represented in the graph. Okay. Now, what I want to do, I want to put this on the graph because there's some other properties that I want to pull out as well. So if I was to stick this on, okay, so we have y, x. I'm only going to find the points that I need. So I need 9. I need 3. I need -3. So my first point, -3, 9. I need 4. So maybe I'll put 4 about here. And then 2. This is -2. 2. So this is 1 and 1. So 2, -2, 1 and 1. So it's probably here. And then 0, 0, then 1 and 1, and then 2 and 4, and then 3 and +9. So this is what my graph looks like. So it's supposed to be a little curve at the end. It's not a V shape. Okay. So what am I noticing? When I have this equation where it's just y equals x squared, or y equals ax squared, the y-intercept is 0. Okay, so let's make a note of that. The y-intercept is 0, but the x-intercept is also 0. Not only that, the y-axis cuts the graph in 2 equal parts. So the y-axis is what we call the axis of symmetry because it splits it in 2 equal parts. So this is the axis of symmetry. Okay, so that's when we have y equals ax squared. So it's nice and behaved, and this is really the basis for all of the quadratic equations. We start here and then we work our way out. Now let's look at another situation, staying on the y equals x squared, but we're going to look at y equals -x squared. What's this behavior going to be? So if I have x, y, and I'm going to pick points -3, -2, -1, 0, 1, 2, 3. My points are going to be -9, -4, -1, 0, -1, -4, -9. The reason why these values are negative is because I'm taking the negative of x squared. So a quick example, y is equal to negative of -3 squared. Well, -3 squared is 9. I want the negative of that, so that's -9. So I do that for all these values. So when I put this on the graph, I'm going to end up with, so there's my 0, so that's both my x-intercept and y-intercept, okay? This is the x-intercept and y-intercept. Because the x-intercept happens when y equals 0, and the y-intercept happens when x equals 0. So this is the point that satisfies both of those. Nonetheless, I'm going to stick this on the graph, so I know I have 3, then I have -3, then I have -9 somewhere, I have -4. So I'm just mapping out the values that I need, and I have -1. Probably not going to be pretty, but we'll deal with it. So I have 0, 0 there. I have 1, -1 about, we'll say there, and then we'll do -1, -1 there. Then I have 2, -4 here, or -2, -4, and I have 2, -4 here. This is really poor graphing. And I have -3, -9, and 3, -9. Okay. So this negative sign turned this graph upside down. So we had our original graph look something like this, right? And so this was y equals x squared. This is y equals -x squared. So we just flipped it across the x-axis. And now, if I compare both graphs based on some of the stuff we said earlier, for this graph, we have a minimum, right? It's right here at 0, 0. But for the graph that's turned up, if it looks like, if you picture a mountain, you climb up one side, you go down the other. We have a maximum. The peak is a maximum. And that also happens at 0, 0. Okay? So whenever you have a negative, and just like we mentioned, it tells you if you have a maximum or minimum based on the sign that's in front of A. And we also have a graph that is symmetric along with the y-axis, so the y-axis still splits it down the middle. All right. So before I move on, let me just intervene with some properties of quadratic equations. So if you notice, this is called, it's a U-shaped graph. It's called a parabola. It's U-shaped. It has a max or min depending on the negative sign, right, in front of A. And then it also has a vertex, which is either a peak or a trough, like the bottommost part. It also has an axis of symmetry, which can be modeled using an equation, x equals a. Okay, so you can picture this as a line that's splitting the graph at some value of x. Other thing that we're going to come across shortly is that not all quadratic equations act around the y-axis. This doesn't always look like that. Okay, it's not always like this or like this. It could be all the way out here. All the way out here. Or it could split the x-axis somewhere. looking like that. It could be really compressed, like really like compressed. We talked about compression before. Or it could be really stretched. Okay, so this green line, if it's a fraction, it's going to push it towards the x-axis. If it's a whole number, you see this yellow line, it's going to squeeze it against the y-axis. So you get all these types of different quadratic equations depending on your A, B, and C. Okay, so what happens when, if you have y equals a x squared plus c, and I'm kind of jumping the gun a little bit. Actually, you know what? Let's not jump the gun. Let's do it one thing at a time. What happens if I have ax squared plus bx? A couple things happens. The graph or the equation will have two zeros. What are zeros? Zeros are x-intercepts, also known as roots. And one of the zeros is 0. This means that one of the sides of the graph, when I say the sides, like I don't know what you call them, one of these parts are going to cut through the origin. So one of the arms will pass through the origin. Guaranteed. One of the arms will pass through the origin. So, and then the other part is, so it has two zeros with one of them passing through the origin. So let's look at a quick example. And hopefully I could get it on the graph. So if I have x and y, and I have y is equal to 2x squared plus 2x, all right, so if I graph the values, -3, -2, -1, 0, 1, 2, 3, if I plug these in, so let's start with what happens if I plug in -3. I'm going to end up with y is equal to 2 times -3 squared plus 2 times 3, which is equal to -3 squared is 9 times 2 is 18 plus 2 times 3 is 24. So this is 24. If I do this for all the values, so I have 24, and then I have -2 squared. And then for 2, I'm going to have, so 2 times -2 squared is 2 times, sorry, -2 squared is 4 times 2 is 8 plus 6, or plus 4 is 12, sorry. And then for -1, I have -1 squared, which is 1 times 2 is 2, plus 2 times 1, which is 4. And then for 0, I'm going to have 2 times 0 squared plus 2 times 0, which is 0. And then I'm going to have for 1, I'm going to have 2 times 1, which is 2, plus 2 times 1, which is 4. And then for 2, I'm going to have 2 times 4, which is 8, plus 2 times 2, which is 4, which is 12. And then this is going to be 24. Okay, so let's look at this again. Something is not quite right. So if it's -3, see, big mistake. Forgot the -3. So it's going to be 18 minus 6, which is 12. So this is 12 And if I do that right, I'm going to get 4. I have 0, 0, 4, 12, and 24. Yeah. So just like I said, we have 2 zeros. When do the zeros happen? These are the x-intercepts when y equals 0. So y is equal to 0 twice. One of them happened at -1, and the other one happens at the origin. One of the arms will pass through the origin. All right, so I'll try and graph this. It's going to be terrible, but it is what it is. So we have 0, 0. We have -1, 0. Then we have negative. Okay, maybe I should. Let's go -1, -2. You know what? Let's just get some real points on this thing. Okay, so let's go with 1, 2, 3. And then 1, 2, 3, 4. It just helps to do this properly. 1, 2, 3, 4, 5, 7, 8. We don't actually need all the points. We just need a couple of them. And all right, so -3, 12. So that's somewhere up here. We'll put it there. -2, 4. So this is -3, -2, -1. -2, 4 is here. -1, 0 is -1, 0. Then I have 0, 0. Then I have 1, 4. Then I have 2, 12. So again, somewhere up here. All right. So the only thing that we're missing is the vertex, which we could find. So it's going to look something like that. That's terrible graphing, but bear with me. So the reason why the vertex didn't show up is because it's actually here. And at this point, it's half. This is at a half. So the vertex actually happens at -1, or sorry, -1/2, -1. Okay. But we're not really focused on that right now, but this is what our graph looks like. So the takeaways from here, if your equation is only in this form, you're going to have a graph that has 2 zeros, and one of them is going to pass through the origin, 100%. That's if it's in this form. All right, let's keep this going. What if your equation, what if you end up with ax squared plus c? All right, so in this case, a lot can happen here. So let's look at the possible scenarios. So remember, c is the y-intercept. So what if c is up here and a is positive? That means the graph opens upwards. So that means we're going to get a graph that opens in that direction. In this case, there is no x-intercept, right? This doesn't touch, this does not, this is away from the x-axis. So there's a rule there. Let's write that down. So number one rule, if a is positive, so if a is greater than 0, so it's positive, and c is also greater than 0, so that means it's not touching the origin. Remember, if c was 0, then we just have, if c is equal to 0, then we just have y equals ax squared. And we know that goes through the origin. If a is greater than 0, and c is greater than 0, there are no x-intercepts at all. Okay. Now, what if a is greater than 0, but c is less than 0? Okay, so a is greater than 0 just means that it opens upward. But if c is less than 0, that means I have a y-intercept that's below the x-axis. So it's opening upwards. So for this special case, if a is greater than 0, but c is less than 0, then there are two zeros, or two x-intercepts. How do you spell zeros? Call it like that. Two x-intercepts. That's not good. Two zeros. All right, number 3. If a is still positive, no, let's look at what if a is negative. We already covered the positive. So if a is negative now, so a is less than 0, which means that the graph opens down. And c is less than 0. Okay, let's look at this. So a is less than 0, so the graph opens down. C is less than 0. That means now we're going this way. So you can clearly see that there are no x-intercepts, or no zeros. And then lastly, if a is less than 0, but c is greater than 0, so a means that the graph is opening down, but c is greater than 0, so the y-intercept is above 0, so I have something that looks like this. Okay, then we have, there are two zeros, or two x-intercepts. There are two x-intercepts. Now, what happens when we have the full equation? I don't need to do an example for this. Just understand that this is, like, even if you build your table of values and map this out, this is what it's going to look like. So let's look at the other case, the final case, where we have an equation that is completely in general form. So for this one, I want to do an example. So I'm going to actually have y is equal to negative x squared minus 3x minus 2. Okay, so just to set some expectations here, firstly, we know this is going to be a negative. It's going to open downwards because of this thing. Right? The other thing that we could expect, so we expect open downward. The other thing we're going to expect is that there should be at least one zero, but we should get two. At least 1 0, but should be two zeros. All right, so let's just build a table of values, and we'll find some values here, and then we will graph it and then study the behavior. So I have negative 3, negative 2, negative 1. You notice I always use these same values over and over. See what I get. So I end up with, let me just test my math, because you know my arithmetic ain't best. So we'll go y equals negative of negative 3 squared minus 3 times negative 3 minus 2. So I have negative of 9. Then I have negative 3 times negative 2, so plus 9. I have minus 2. So those 9s cancel out, so I end up with minus 2. Okay, so that's good. So I have minus 2. I have 0, 0, negative 2. Then I have negative 6. I have negative 12. And I have negative 20. So before we even go to the graph, let's look at what we have. I have two x-intercepts, right? These are my zeros, right? Because y is equal to 0. And then I also notice I have a y-intercept where x equals 0. And what did I say was going to happen? Well, the graph is negative. I see all my y values are negative. So I expect it to open downwards, check. There's at least 1 0, but there should be 2. So there's 2. Okay, and then just from previous thinking, we know that our y-intercept is just c, and our y-intercept is c. It's -2. It's right here. Okay, good. So let's see what this looks like on the graph, and then we'll compare it to what we were getting for y equals x squared, which is our root equation. So I'm going to put more emphasis on the negative values in my graph, so leave more room for that. Even though, you know what, I'm not going to take all of them. I'm just going to take a few. So -1, -2, -3, -4, -5, -6, -7. And then for x, I know I have 1, 2, -3. Then I have 1, 2, 3. All right, do I have anything above? I don't have anything above that. So let's graph it. So I know I have a y-intercept. Let's just, so -3, -2 is -3, -2 is here. Then I have -2, 0. Then I have -1, 0. Then I have 0, -2. Then I have 1, -6. 1, -6. This means that if I added a -4 for x, I would have gotten a -6. So let's see. -4 squared is 16, so -16 plus 12 minus 2. So this is -4 minus 2, which is -6. So I just did that so I could get my graph to work. So the -6 is over here at -4. So when I put that together, my lord. Put that together, and up with something that looks like this. So I know that the axis of symmetry happens there. So this looks like it's -1.5 x when x equals -1.5. That's where the axis of symmetry is. So that's x equals -1.5, which means that the vertex looks like it happens at -1.5 and 1. I don't know what this value is. It's probably 1. And there's ways to figure that out, and we'll get into that some other time. Okay, so that's your introduction to quadratic equations. Stay tuned for other topics, because as I mentioned, there's lots of topics or lots of areas to cover in quadratic equations.